Thank you very much, Professor Yu, for very kind introduction. Can you hear me?
Yes, sir.
Okay. So, and it is my great honor to have this opportunity to present our research results or our research progress on tsunami-induced seawater intrusion and aquifer recovery. And this topic is in collaboration with Dr. Jiaki Ryu, our postdoctoral researcher. And okay, let me start my presentation. Okay, so let's start from a simple coastal groundwater system. So this figure is showing what is called unconfined aquifer system nearby the coast. And the groundwater discussion is quite important in coastal areas because around 41% of the world population live within just 100 kilometers from the coastline. So and also the freshwater resources are very important issues for us. So how we can properly manage groundwater in coastal area is a big issue for human beings. And we have been working on seawater intrusion horizontally because of the pumping induced seawater intrusion from seaside toward the landward side. However, recently, we experienced at least two serious tsunami disasters and recognize the another important uh, processes which affect the stability or the sustainability of the fresh groundwater nearby the coast. That is tsunami. And this is another schematic figure showing how tsunami affect fresh groundwater nearby the coast. I explained the horizontal seawater intrusion by pumping induced processes. And another very big issue by tsunami induced seawater intrusion is vertical intrusion. And this can happen either tsunami or the big storm surges at the time of typhoon or other serious weather event. We recently gotten very huge typhoons in Japan and also in Korea. And nearby the coastal area, the storm surge induced vertical seawater intrusion could be the issue for the freshwater resources conservation. So that is the main reason why we have been working on this vertical seawater intrusion processes after tsunami. And these four figures are kind of schematics which we think important for considering the tsunami-related freshwater groundwater interaction nearby the coast. Okay, the upper left is during the flooding. And of course, seawater comes on top of the land area and then start infiltration through the land surface. And in some cases, if we have an open wells, then the open well is a direct pathway of seawater to go into the subsurface aquifer. And that kind of problem happened at the Indian eastern part of the Indian coast after the Sumatra earthquake. There were a lot of open dug wells nearby the coast in eastern coastal area, and the majority of these wells were suffered by direct um, transfer of seawater through the open well to unconfined aquifer systems. And third one, this has not been well studied, but may if we have an unsaturated zone, then because of the very rapid flooding, part of the unsaturated part air can be pressurized and then behave very differently. But this part of the science has not been well studied. So that this is an open question for the next stage. Okay, so this is a kind of the processes which we should consider during flood. And immediate aftermath, hours to days of flooding, of course, infiltration continues. Open wear in process is also continues. And then another thing which might be important is the ponding of seawater in depressions. And that ponding may continue longer period of time and then continuously infiltrate seawater to subsurface. And that causes a long duration effect of freshwater salinization, fresh groundwater salinization. And then the third stage, which we are thinking about, is the fingering of the seawater to freshwater groundwater part in subsurface. And this happens because of the density differences. Denser seawater comes on top of the fresher groundwater, and because of the gravitational instability, then fingering starts to happen to further contaminate fresh groundwater. And this fingering makes the mixing very fast compared with the normal exchange of water, and that also affects the sustainability of fresh groundwater. And long-term aftermath, years of flooding, then the precipitation can move salinized water back to the sea by groundwater flow. But if your bedrock shows this kind of undulation, again, because of the density contrast, denser water may stay in the terrestrial part of the aquifer and continuously contaminate freshwater, expected freshwater as saline. So these are the processes which we think important, and as you already recognize, to solve these issues, geology, hydrogeology, and engineering, geophysical exploration knowledge are necessary or the must to work with. So this is one example again from the Tohoku earthquake. After several months, I think after 5 months of the tsunami, we still observed this kind of saltwater ponding in the area. And the very slow continuous infiltration from this salty pond to downward continuously contaminate groundwater. And another issue which we observed after 8 months of the tsunami was the crystallization of salt in topsoil. So once the seawater goes through the unsaturated zone, the part of the salty water stays in the unsaturated part, and by slow drying processes, then the oversaturation of salts start to happen, and then crystallization, precipitation of salts. Yeah, precipitation of salts start to happen. And this can again make a delayed contamination of groundwater by dissolution of this salt by precipitation. So this is a very complicated, complex processes, but very interesting process from science and engineering, geological sciences, and hydrogeology again. And this is one example which I took from the groundwater specific conductance, electrical conductivity after the 2004 Indian Ocean tsunami. And okay, this is the tsunami event, and we observed a very rapid increase of electrical conductivity of well water, and this very much higher. This is very much higher than the drinking water standard set by WHO. So this is 1 year period. So you can see that at least 1 year or more than 1 year were necessary for the groundwater to return to be able to drink. And this is another example what happened after the Tohoku earthquake year 2011. And this, okay, this dashed line, yes, this line is the time of the tsunami. And we again observe the very rapid increase of the specific conduction, electrical conductivity of water. And that also, yes, became much higher than the drinking water standard. One interesting thing which you can recognize from this figure is the recovery of electrical conductivity of water is not monotonic. Sometimes electrical conductivity reduces very much and became lower than drinking water standard. But again, it increased and then decreased. And one of the possible interpretation of this zigzag like change of electrical conductivity, specific conductance, was because of the dissolution of salt crystals, which I explained, and also continuous seawater infiltration from the pond. So it is not such straightforward for us to expect the groundwater to be recovered to fresh with time. So we need to know what are controlling these kind of zigzag patterns and how long do we need to anticipate for the groundwater to return to original, this fresh condition. So again, the subsurface science, engineering geology is important, I believe. And one strong method to work with this kind of process is numerical modeling. And these are the equations which we have been using for analyzing the tsunami-induced seawater intrusion processes. The main processes are fluid flow, groundwater flow, and mass transport processes, and the density-driven flow. Because seawater is denser than freshwater, and that density difference itself becomes a driving force for water to move. So these three processes are necessary, plus unsaturated zone processes above the water table is contributing to the short-term and long-term contamination processes by tsunami and storm surge induced seawater infiltrations. And our group has been using the software named FE-Flow from DHI, but I am not a salesman for the FE-Flow. So you can use any software which can handle these kind of processes, or even you can write a code from the scratch to work on this kind of processes. And this is a summary of the current state of numerical modeling approaches for this kind of tsunami-induced groundwater contaminations. And yes, there have been a variety of researchers all over the world working on these issues. And our group are also one of the groups working on numerical-based studies on tsunami-induced groundwater processes. So those who are interested in our activities, please visit Dr. Liu and my papers recently published, and also these papers which have been working on these issues. Numerical modeling is a very strong tool, but we need to go through the processes to make the modeling reasonably well explain the process and reasonably well predict or forecast the future processes. First thing which we need to do is model conceptualization, what kind of processes we are interested in, and which part of the groundwater system we want to work with. that kind of conceptualization is the first step, and that is very important. And then defining the conceptual model, then we start to gather necessary input data and also the parameterization. And then after these processes, then we do a numerical simulation and then calibration and then evaluating our results. So I will show you several steps which we took to prepare these kind of parameterization and modeling processes. This is kind of another interesting tips for us to work with subsurface environment. So first of all, for us to work with groundwater flow, we need to know how permeable the aquifer is and how much amount of space are prepared for groundwater to be in the system. That is effective porosity. And the island setting is quite unique because tidal signals is a kind of perturbations for this groundwater system. So we can take advantage of having that kind of tidal signals to estimate the parameters of the coastal areas. And Professor Aichi, he is also one of my colleagues, established the analytical solution for using this tidal signal to estimate permeability divided by effective porosity. And this is one example of the data which we used. And upper part is the tidal signal. And lower part of the data are the well water level fluctuation temporal. And by doing a fast Fourier transform of these two data, we get a very clear tidal signals from tide. That is obvious because this is tidal signal. So we can get a very clear 4 peaks of the tidal signals from the seawater, sea level fluctuations. And from the well fluctuation, this data, we can also detect the very clear peaks of the tidal signals of the well water levels. So this is a kind of input-output system. So we can use this information to estimate the parameters which is controlling how much amount of amplitude decay occurs and how much amount of phase shift occurs in the aquifer system. Then we can get the information related to hydraulic conductivity divided by porosity. This is a root mean squared error map of the hydraulic transmissivity's thickness of the saturated zone cross plot. And this figure is showing that the tidal signal analysis is really not sensitive to the thickness of the saturated zone, but is very much sensitive to the hydraulic transmissivities. So we can get the information of hydraulic transmissivities of the island by tidal analysis to be very narrow range. And also we can use the analytical solution to estimate the recharge divided by hydraulic conductivity by a very simple analytical model. This has been developed by Go and Zhao in 2007. And by using this model and compared with our water table elevations in the island, we can narrow down this parameter, precipitation or infiltration to groundwater divided by hydraulic conductivity to two factor of 2. So we can really very narrow down the possible lumped parameter by this kind of application. And then we further fine tuning the parameters by fitting the well water level and the numerically estimated water table elevations spatially to finally uh, determine the parameter of the aquifers of the area of the study. So this is how we use the measured data for the necessary parameterization for the numerical simulation processes. So from now on, I would like to talk about the real case study of the island that is named Nijima Island. Nijima Island is named from the new island. And this island was really formed very recently. And the location of Nijima is here. This is Tokyo, and this is plate boundaries, what is called plate boundaries. And as you know, Japan is located in the very complicated plate boundary settings, and Nijima is here. And this red line is a trace of the Nankai Trough, which is anticipated to trigger or to cause a possibly magnitude 9 earthquake, and that would cause a serious tsunamis along the western part of Japan. And also this Nijima is located east of the Nankai Trough. So this island was also anticipated to get in a tsunami hazard. And right-hand side figure is the topographic map of the island. And here, in between these two high elevation mountains, the local residents are forming the villages, and they're living in that area, in principle in this area. And this island is a very scenic island. And yes, I have never visited the Jeju Island, so I don't know which one is better, but I would recommend you to visit Nijima Island if you have chance to come to Japan. This is really scenic place, but this is kind of sightseeing place for and attract a lot of visitors. But this red area were the possibly tsunami affected zone if the Nankai Trough earthquake happened. And this island, this is the view of the Nijima Island, Honson village, and main village in the island. And I took these photos from north toward the south. So this coast is the western coast, and this side was very possibly would be affected by tsunami near future by the Nankai Trough earthquake. So this area would be inundated, and this village would be destroyed. That is my anticipation, unfortunately. But as you can see, both in south and north, there are high mountain areas, and they are very well trained to the evacuation. So I would expect that no human deaths would happen in this island if they properly behave. But the village would be destroyed and the groundwater system would be affected. And this is the anticipated tsunami wave height along the coast of the western part of the Japan. I'm sorry that these characters are in the Japanese, but please take a look at these spikes here. And blue one is the anticipated maximum height of the tsunami wave height at the time of the Nankai Trough earthquake. And this peak is the place where the Nijima west coast is. So under the very worst cases, maximum height of the tsunami wave at the island can reach to 30 meters. And this is peninsula, and this is Shima City, which is Wakayama Prefecture, western part of Japan. But Nijima is one of the most possibly affected island in Japan with respect to the Nankai Trough induced tsunami. Okay, so let's move on to the geology of the island. As I mentioned, the name of this island is Nijima, and Nijima is the new island. And this part, northern part of the island was old, but this southern part was formed by the eruption 886 AD. So that means around 1200 years ago, by very serious rhyolitic eruption of the Mukaiyama volcano. And very early stage of the rhyolitic volcanic activities, pyroclastic surge deposit and pyroclastic flow filled the area between this Mukaiyama volcano, newly formed volcano, and the old volcanoes, and then form this island. So this is macroscopically single-layered unconfined aquifer formed 1200 years ago. So this is very young sediments, and hydraulic conductivity is quite high, and rainfall is also very high in this area. And because of this setting, water supply of this island and next island here was solely from groundwater of this island. And these blue dots are the public wells dedicated for the area of the water supply. So this is the general setting of geology. And you can see this is the eastern coast of the island. And this white material are the pyroclastic surge deposit, which was suddenly deposited, let's say suddenly deposited geologically at 886 AD. And yes, you can see how you can I? Oh, actually, this is a video. I don't know how I can stop pointer option, or I'm sorry, I'm not good at working on that. Maybe just wait a minute. I think if I do this, yes, yes, this kind of very unconsolidated sediments is the aquifer material. So you can understand that the hydraulic conductivity values of this aquifer can be very high. Oh, okay. I know now how I can work with. Okay, then again. So this is the estimation by Tokyo Disaster Management Council that the tsunami may run up almost to here. So this area, Honson Village, will be very strongly, seriously affected by tsunami. And on this island, of course, they recognize that they can get a tsunami, so they prepare for that. And the current preparedness is, yes, written here, the 3-liter bottled water per person per day for 3-day emergency has been reversed. So that means around 10 liters of bottled water are prepared. But that is only for drinking. And also, as I mentioned, this is a very scenic touristic place. So for example, in summer high season, maybe let's say more number of people than the residents will visit this island. But the local officers are not considering these kind of temporary visitors. So even though they mention that, okay, 10 liters of bottled water are prepared, I have a big concern that this amount of preparation is not enough for this part of the island. So that is another reason why we want to work with this island whether we can provide a possible good solution for the local communities of using groundwater after the tsunami disaster. So this is the numerical simulation results of the tsunami inundation. The upper left figure is the situation before the tsunami. So you can see, yes, these white arrows are flow lines. So precipitation comes vertically down to the water table. Water table is black line, and then flow both ways. And at the time of tsunami, seawater, this red one is seawater. Seawater infiltrates very rapidly, vertically down, all the way to the original water table, and then stores seawater in the unsaturated part of the island. And this is very important message for the local people and also the hydrogeological community. In the case, hydroconductivity values are high, then water table can be become lower, because flow is very efficient to discharge water out to the sea. So water table can be low, hydroconductivity can be high. So this space for temporal storage of seawater in unsaturated zone is huge. And that area are used for storing seawater, and just 10 minutes are enough for seawater to be stored in this area. So this right-hand side figure is showing the temporal change of total amount of salt mass entered through the land surface to subsurface. So 10 minutes is, yes, very much enough for 70% or 75% of the total salt mass to enter. And 1 hour is, yes, almost all the necessary time for the initial seawater storage in subsurface originally unsaturated zone. And then that seawater start to contaminate or fresh groundwater. And this is 80 days after the tsunami. And you can see this kind of very complicated flow lines. And that happened because of the fingering of the seawater to go down to the originally freshwater and contaminate majority of the freshwater in the western part of the island in this case. And then after 2 years, we still have saline water here, and moving this mass of water slowly toward west to be discharged out. So again, right-hand side figure is showing the time versus total mass of salt in subsurface. And you can see in this case example, it will be necessary for more than 10 years for the salt mass to be discharged out by precipitation. So we need to think about really long-term recovery processes for us to think about the possible usage of groundwater in contaminated area. Then another question which we need to think about is which part of the aquifer would be contaminated and which part of the aquifer would be survived by the tsunami event. So for that purpose, we developed a three-dimensional numerical model of the island like this, and then run the numerical simulations. And these figures are showing how groundwater is contaminated and recovered. And in this case, we assume the rather higher tsunami wave height. Then in this case, part of the contaminated water moves toward the east, not only for the west, but also for the east. So again, coming back to the previous figure, the basement shape was estimated to be this shape. So if the tsunami goes over this crest of the basement, then the infiltrated water moves this way toward east. So even though tsunami come from the west, groundwater would be contaminated even toward the east in case if the basement structure is something like this. So knowing the basement structure is very important for us to think of the groundwater survivor with respect to tsunami. But in any case, you can also observe that in the southern part of the island, oh, sorry, not good. Yes, this part would not be affected. So we can see that the unpolluted portion of the groundwater exists. And that part of groundwater may provide the water supply post-disaster period of time. So even though the current local preparedness is rather small, but this island would take advantage of having another freshwater source in the southern part of the island to be able to use for the post-disaster recovery activities. So another important thing with respect to the bedrock structure is, again, the bedrock structure is the key for the freshening processes. So the upper part of the figure is showing the current estimation of bedrock structures. But if the bedrock structure is something like this, the basin type, then the seawater would stay in the bottom of the basin and then continuously contaminate groundwater. So knowing the basement structure is again very important for us to think of the scientific processes and also the considering the preparedness with respect to the disaster in the local community point of view. So we have been working on the, geophysical exploration activities such as electrical resistivity survey. And this is me when I was young. And we did an electrical resistivity surveys on the island. And yes, we did a rather simple 1D resistivity measurement and estimated the structures, dry soil, unsaturated part, and freshwater and saltwater based on this inversion. And this right-hand side figure is a comparison between the 1D resistivity survey and 2D, 3D numerical model. And you can see that the location of water table is more or less very similar, and the freshwater saltwater interface depth is also rather similar. So this is another important information for us to calibrate our model and also get an structural information. And another approach which we took is what is called micro-tremor survey. And we put in a number of seismometers, red dot here, and measure the surface waves. And we use the dispersion phenomenon of surface wave to estimate the S velocity structure in subsurface. And this is the measurement. Blue one is the measurement and red one is the analysis. And we get this kind of S wave velocities, structures. And this low S wave velocity is the pyroclastic surge deposit. That is our interpretation. So this is a bedrock depth estimated. However, we are not still certain whether our results are very accurate or not. Sorry. These white contours are the estimated bedrock surface elevations by Professor Shindo. And we, in principle, borrowed this result for our numerical simulation. So this is a crest, highest part of the bedrock structure, and then bedrock dips toward this direction and toward this direction. And we did a micro-tremor survey here in red dot. And some of the results are consistent and some are not. So that part of the information is not perfect still. So we need to further characterize the bedrock structure to better provide the information to the local community. However, this pattern, the bedrock structures becoming shallower towards south, are consistent between the one by Sindo and also the ones which we measured by we estimated from micro-tremor survey. So the southern part of the bedrock structure would be higher, so dipping toward the north. So this part, aquifer material or groundwater in this part would not be affected by the tsunami. That part of the conclusion won't change. So we think that current information strongly suggests still the existence of fresh water in the southern part of the island, which can be the site for the water supply after the disaster. And we have been communicating with local authorities, and these right-hand side photos are the figures the young students, researchers are working on. And this is the Dr. Jackie Liu when he was very young. And these are the elder group, myself and the local authority people and my another colleague working on collaborating with how many years? Almost 30 years of period. So this is old age team and this is young age teams. But anyway, we conducted a field survey with this kind of group and also communicate with local authorities. And the current preparation in a 3-liter bottle of water per person per 3 days, again. So we consider the necessity of or importance of understanding the behavior of aquifer for possible usage of groundwater after the disaster, because the local authorities mentioned that after 3 days, they may have to rely on the rescue from mainland Tokyo. But I do not think that kind of rescue is effective, because if the Nankai Trough earthquake happened and tsunami happened, the mainland Tokyo also would be affected. So I strongly suggested the local authorities to think of self rescuing processes just after the disaster. And for that purpose, think more seriously on the possible freshwater resources. And we reported our research result and also our limitations to the local authorities. And what we suggested to them is a part of the aquifer at least can be used for freshwater resource even after the disasters. And our analysis has an uncertainty because of the lack of the accurate bedrock structures. So we suggest them to think of better estimation of the bedrock structures for this purpose. But still, we can say that very possible water supply from southern part of the island is possible with enough amount, and suggest the preparation of pumps, generators, fuels, and clean containers at the well site in the south. And local authorities are kind enough to acknowledge our suggestion and has started their action. So that's how our engineering geology, hydrogeology, and the subsurface engineering science could contribute to the society. So this is a kind of one example going on in Japan, but I think we can, yes, both in Korean colleagues and Japanese colleagues can think further on the collaboration and sharing our ideas and knowledge to contribute to the society and also science. So this is my presentation. Thank you very much for your kind attention. Thank you.